In this lesson, we will describe the properties of acids and bases, define an acid and a base according to both the Arrhenius and Brønsted-Lowry theories, and identify the conjugate acid-base pairs in looking at a Brønsted-Lowry acid-base reaction. We can find acids and bases all around us. Examples of acids include juice, vinegar, citrus fruits, and sodas. Examples of bases include cleaners such as Drano or Windex, soap, and baking soda. Acid and base reactions are often called neutralization reactions. An acid and a base produce a salt and water, which are generally neutral. For example, HCl is an acid, NaOH is a base, and we produce NaCl, which is table salt, and water. Another example is HNO3, which is an acid, BaOH2, which is a base, barium nitrate, which is a salt, plus water. As we look at acids and bases, we will often use the abbreviation H+. In reality, what we have present is a hydronium ion, which is a water, H2O, with an extra H+, which is also known as a proton. There are several different definitions of acids and bases. We will discuss two of them. The first is Arrhenius, and an Arrhenius acid produces H+ in water. Remember that H+ and H3O+ are the same thing, it's just two different ways of writing it. So HCl in water will produce H3O+ and Cl-. An Arrhenius base produces OH- in water, so NH3 plus H2O yields NH4+ and OH-. While Arrhenius acids can be easy to identify when we see how they behave in water, it's not always the best definition. Arrhenius is very limiting because it requires that something be in water. While most of the things we will look at are in water, what we will find is that we need a broader definition to better understand and assign something as an acid or a base. For that, we will use the Brønsted-Lowry theory. In this case, an acid is a proton donor and a base is a proton acceptor. Remember that a proton is just an H+. HF donates a proton to form F-. Notice that we lost the hydrogen and we also lost a plus charge because we started at 0, so it's going to go down by 1, and we end up with F-. This is known as a conjugate acid-base pair. A conjugate acid-base pair always differs by a single proton. When we look at water, we see that water accepts a proton to form H3O+. We've increased the number of hydrogens by 1, and we've increased the charge on the species by 1 from 0 to +1. Remember, conjugate acid-base pairs always differ by a single proton. We see that here with HF and F-, as well as with H2O and H3O+. We can also look at the reverse reaction. H3O+ donates a proton to form H2O. In going from H3O+, we lose one hydrogen, and the charge goes from plus to 0, so the charge was reduced by 1. F- is acting as a base and accepts a proton to form HF. The F- gained one hydrogen and the charge increased by 1 to form a neutral HF molecule. In this case, HF is acting as an acid because it was a proton donor in the forward reaction, and F- is a base because it's a proton acceptor. Looking at the water, it acts as a base in forming H3O+. H3O+ acts as an acid because it's a proton donor. Since H3O+ and HF are willing to donate protons to some other species, we see that they are considered acids. H2O and F- are willing to accept a proton, and therefore they are considered bases. Conjugates are always one acid and one base. When looking at an overall reaction, we see that the left side has one acid and one base, and the right side will have one acid and one base. Which substances act as an acid in the reaction? H2O donates a proton to form OH minus, so it's acting as an acid. It goes from H2O to OH minus, so we lose an H and lose a plus charge. NH4 plus also donates a proton to form NH3, so we lose an H and a plus charge from NH4 plus. So these two substances, the H2O and the NH4 plus, are acting as acid because they are willing to donate a proton. Which substances act as a base in the reaction? When we look at NH3, we see it's willing to accept a proton to form NH4 plus. NH3 gains a hydrogen and a +1 charge, so they differ by a single proton. OH minus accepts a proton to form H2O. We look at this in the context of a reaction to see how something is behaving, whether it is accepting or donating a proton, to determine whether it's a base or an acid. Water is amphoteric because it can act like an acid or a base. It can either donate a proton or accept a proton. In the first example, we see that HF is an acid because it's donating a proton and as a result forms F-. Since HF is giving up the proton, it's considered an acid. H2O is acting as a base because it's accepting that proton to form H3O+. NH3 acts as a base because it's accepting a proton, and water acts as an acid because it's donating a proton to form OH-. Whether water is acting as an acid or base will depend on what it's partnered with. Remember, acid-base conjugate pairs always differ from one another by a single H+.